In this video, we are going to talk about first-order differential equations that are what we call separable. Let's see what a separable differential equation is. A first-order equation is separable if it can be written in this form. dy dx is equal to a function of x multiplied by a function of y. So this is the product of these functions. And as we have talked about in the past, we defined dy dx as a function of variables x and y. So if we can write that differential equation as a product of those two functions, then it is separable. So let's take a look at this first example, dy dx, and we'll go ahead and factor an x out of that numerator. And as you can see, we have here that this is x multiplied by 2 plus y over y squared plus 1. So as you can see, we have a function of x multiplied by a function of y. So we have a separable differential equation. However, in our next example, we cannot factor. We cannot write dy dx as a function of x multiplied by a function of y. Therefore, this is not a separable differential equation. Okay, so how are we going to solve a separable differential equation? So once we have a separable equation, basically what we're going to do is we're going to separate the differentials. We'll write dy as a differential and dx, and then we will go ahead and take this p of y and divide both sides by p of y, and you could look at it as defining h of y is 1 divided by p of y, and now we have a separable differential equation. Excuse me, now we have separated the variables. This is a separable DE. Okay, and now we're going to integrate both sides. So you could think of separate and integrate. Okay, so as you can see, we're going to integrate both sides, and we will come up with the antiderivative of the left-hand side is equal to the antiderivative of the right-hand side, and we're going to combine both constants of integration on the right-hand side, okay? And that's customary. Okay? Well, let's give it a try. Let's look at our first example. dy dx is equal to x minus 5 divided by y squared. So let's go ahead and treat dy dx as differentials. So we have dy here in the numerator, and we have dx on the right-hand side. Now we'll go ahead and bring the y squared, multiply both sides of the equation by y squared, and we still have an x minus 5 on that right-hand side. So we have now separated our variables, and so now we are going to integrate. So separate and integrate. Okay, so now we'll go ahead and integrate the left-hand side. We have 1/3 y cubed. Again, we're going to bring that constant integration on the right-hand side and just combine them. And then we have 1/2 x squared minus 5x plus our first constant of integration. Now we can go ahead and multiply both sides by 3. And here, this 3c, we can go ahead and write that as we'll call that C1, and that's C2. So C2 is equal to 3C1. And now all we have to do is take the cube root of both sides. So y is equal to the cube root of 3/2 x squared minus 15x plus c. And of course, c is that second constant that we have. So what we could actually do is get rid of that second one and just call that our c, since that is going to be our last constant. So we usually use c for last constant, or for the constant in our solution. Okay, so this is the general solution. So and there are infinitely many solutions represented by this general solution, one for every value of c. Okay? If we look to the right, you can see that all of the solutions, some of the solutions are represented here. So you can see this is the solution when c is 24. Here's one when c is 12. Of course, we used c. And here is the solution when c is equal to 0. And so forth. Okay, let's take a look at the next example. dy dx is equal to y minus 1 divided by x plus 3. You can see right away that this is a separable differential equation. We can have 1 divided by y minus 1 dy is equal to 1 divided by x plus 3 dx. Once we've separated, we can now integrate. By the way, this is an IVP. We have our DE and we have our initial condition. So we have an IVP. So when we solve this, we will come up with a particular solution. Instead of a general solution. Okay? So now we have our left-hand side as the natural log of y minus 1, absolute value of y minus 1, is equal to the natural log of the absolute value of x plus 3 plus our first constant that we come across. Okay, so now we can exponentiate both sides. Now this entire right-hand side is in the exponent. So we have the absolute value of y minus 1 is equal to, and I'm going to take some time to show you this. This is equal to the absolute value of x plus 3 times e to the c1. Okay? However, since e to the c1 is a constant, we can now write this as the absolute value of y minus 1 is equal to c2 multiplied by the absolute value of x plus 3. And of course, c2 is equal to e to the C1. Again, we are solving for y. So in order to remove the absolute values, we have to write plus or minus this right-hand side. And then, of course, we have C3 multiplied by the absolute value of x plus 3, and C3 is plus or minus C2. Continuing in the same fashion, we are now, remember, we are trying to solve for y, so we will add 1 to both sides. And as you can see, we have y is equal to C3 multiplied by the absolute value of x plus 3 plus 1. Since this is our last constant, we can go ahead and take that C3 off and just have that C is equal to plus or minus C2, and this is C multiplied by the absolute value of x plus 3 plus 1. Now we could have removed, let's go ahead and do that, these two absolute values, since we did plus or minus that both sides of the equation, and now we have our general solution. Okay, now in order to find the particular solution, we're going to find the constant. So we're going to use y of negative 1 equals 0 to find our constant. Okay. And plugging that in. We will have 0 equals c multiplied by negative 1 plus 3 plus 1. So we have 0 equals 2c plus 1. So we have negative 2c equals 1, and c is equal to negative 1/2. Therefore, y is equal to negative 1/2 times x plus 3 plus 1. And this is our particular solution. Our solution to the IVP. Okay, let's take a look at our next example. dy dx equals the expression shown on the right-hand side. We can see that we have a separable dE since we can multiply both sides by the cosine of y plus e to the y. dy equals 6x to the 5th minus 2x plus 1 dx. So we now have separated the dE. Now we will go ahead and integrate. And here we have the sine of y plus e to the y is equal to x to the 6th minus x squared plus x plus a constant. Now, as you can see here, we cannot solve for y. So consequently, we will have an implicit solution here. So this is our solution. And we could write, since we can't solve for y explicitly. Okay, so some of our solutions to our differential equations will be implicit. I might point out that this is a nonlinear first order differential equation, and a lot of those cannot be solved explicitly.